All right, everyone, welcome back. It's time to dive into one of the most fascinating and fast-evolving fields, quantum technology. So now, before we get started, let's address the elephant in the room. Or should I say, the quantum superposition of an elephant being both in and not in the room at the same time. Did anyone get that one? But yeah, quantum mechanics can be mind-bending, but that's also exactly why we're here today, to demystify it and explore the real-world potential of quantum technology. To help us navigate these questions, we are thrilled to have an inspiring keynote by Sam Stanwyck from Nvidia, a leader at the forefront of quantum advancements. So everyone, please join me in welcoming up on stage Sam Stanwyck.
All right, so I'd like to thank the organizers for having me. It's a pleasure to be here and talk about quantum computing with all of you. And I'll say we do have a panel after this with some real experts who are actually building quantum computers. So I'll try to go quickly and give them plenty of time to go into the details and tell you about what they're doing. So I'll just kind of briefly talk about how we see it at Nvidia and what we're doing to try to realize the great potential of quantum computing. And this slide that looks like I drew it in pencil with very little information on it is supposed to represent kind of the history of computing revolutions with a focus on maybe the past 20 years. So for a long time, we had Moore's Law, and CPUs were improving and improving and improving year after year after year. And we could run more powerful things with computers every year without too much effort based on that. That has slowed down and stopped. But a few kind of revolutions or new scaling laws have taken their place over the last 20 years. The first is the use of accelerated computing for scientific computing applications. So this is starting 20 years ago with GPUs going from something that was used for video games to something that could be used for simulating chemistry or simulating biology and becoming integral in supercomputers that were previously only CPUs. Then maybe starting 15 years ago and ramping up over the decade, we had deep learning, starting with the breakthrough of AlexNet and going into recommender systems and almost every application. And then, of course, we have generative AI. And what these things have in common, at least from an Nvidia perspective, is we tried to work on them, or did work on them, for a very long time before they became valuable, sometimes many, many years. And we did so in partnership with the leading researchers and leading groups in the world with a focus on not dominating ourselves, but with trying to make them successful. So whether that's scientists using CUDA or the researchers at the University of Toronto who came up with the breakthrough of AlexNet, or the group at OpenAI who got the very first DGX in 2016, we try to get in ahead of computing revolutions, figure out how our technology can help, and support the entire ecosystem in pulling in the timeline to make those possible. Another thing that these all have in common is they built on each other. So the groups that made the breakthroughs in deep learning were groups that were already developing with GPUs and taking advantage of them for HPC applications. Generative AI came out of leading deep learning groups. And similarly, we expect that quantum computing, as a future computing revolution, the groups that are going to, many things need to happen, but we expect that the groups that are going to be able to realize it fastest are groups that take advantage of everything else computing has to offer. And we're trying to help make that possible and make that easier. So this is the best one-side summary of what we're doing in quantum. We at least try to be the only quantum computing company that works with every other quantum computing company, be they building quantum hardware building software, researching applications, everyone from academia to supercomputing centers to some of the largest companies in the world. So we have hundreds of quantum partners at this point, all making use of our accelerated computing and AI platforms in some way to advance quantum computing research. And this is where we think that we're going. And the other reason quantum computing is so exciting to us, because for the non-experts in the room, the consensus is quantum computers are not going to be successful alone. They're not going to be good at everything. They're going to work together with the best of other computing technologies, accelerate the parts that they're good at, and integrate in kind of an analogous way to how GPUs integrated into previous CPU-only supercomputers. And those supercomputers are also going to benefit quantum computers. So AI has many benefits to bring to quantum computing. So we see it as kind of a symbiotic, harmonious relationship that's going to help us solve important problems in the future. And on the path there, we also think that there's a lot that we can do. There's been a lot of kind of prognostication of the timeline to useful quantum computing. I don't think that question is necessarily so interesting because it implies passivity when we do have the chance to change it quite a lot by things that we do. So we kind of think of it in terms of challenges that need to be solved to get to useful quantum computing. And that looks like, among many other things, obviously improving quantum hardware from where it is today, but also developing better algorithms, scaling quantum error correction, and solving the systems and infrastructure challenges that go into building an accelerated quantum supercomputer. And we're working on all of these, and we're trying to work on all of them now at the same time, because we'd like to solve these in parallel, help our partners solve them in parallel, to pull in the timeline to useful quantum computing. And on the way there, AI supercomputing is going to enable quantum computing research and help solve almost all of these problems. So whether that's kind of offline in terms of helping to develop algorithms and helps in terms of helping to develop better processors, develop better quantum error correcting code, or as part of the computer in a quantum computing deployment for things like real-time quantum error correction, for things like calibration and control of the quantum computer, and of course for hybrid algorithms and applications. So this is, going back to 2 slides ago, really a symbiotic relationship where quantum computers are going to accelerate the supercomputers of the future and solve problems that CPUs and GPUs today can't and never will. But these systems are also going to be essential in helping the quantum computers get there. And so that sort of that connection is really exciting to us and why we think we're in a good position to help everybody and really make an impact in quantum computing. We have a platform for quantum computing. And so if you're familiar with Nvidia's GPU platform, it's based on a programming model called CUDA, which in short made it so if you knew how to program in C or C++ or Python, you could program a GPU, where before you had to be kind of a real expert programming in the equivalent of assembly code. And that was really critical for GPUs to start making an impact for scientific computing applications. We think that there are a lot of the same needs in quantum computing. Today we have many different modalities of hardware, different programming models. Most of them are programmed today in the equivalent of assembly code. And that is sort of what's needed to make progress in a sense. But long term, first of all, we need a way for chemists and biologists and AI researchers to make use of quantum computing without having to become quantum physicists. So to use it just as another accelerator. We need a software architecture that is built for this kind of tight integration where the classical supercomputer is benefiting from quantum computers, and you can do things like within a quantum function make use of GPU acceleration for quantum error correction, which is highly non-trivial and takes dedicated software. We expect people are going to want something that's hardware agnostic. So, whether it's whatever the qubits are made out of, whether it's superconducting, neutral atom, trapped ion, photonic, or many others, it would be nice if you didn't have to write completely different code in order to program that. It'd be nice if you could write the same thing once and test it in simulation, and then program any different type of quantum computer. So that's why we created CUDA-Q. It's open source software. It's also open at many different levels. We have simulation libraries that are available separately, so anybody using any different framework can also take advantage of them. We have a reference architecture for tightly coupling the quantum computer to GPUs, which is also available separately. And the reason that slide at the beginning is so populated is because of this exactly. We try to not build a walled garden, but expose our whole platform so that quantum companies and quantum researchers can take advantage of it in whatever way they find useful. And this little green box at the bottom, which I'm struggling to highlight, is maybe the most important part. This all builds on everything else that NVIDIA does. So by using this, you have access to anything else you can do with the GPU, all of our software, all of partner software that we optimize, together with anything that you want to do in quantum computing. And we think that this is going to be really important for making the breakthroughs that we need to do. I'm going to talk about two quick examples of things people are doing with our platform, and then end it and get the panel going. The first is around improving quantum processors. So if you don't know, pretty much everything that you would like to run on a quantum processor today is limited by noise. Quantum bits are sensitive to noise in a way that classical bits are not. Because of the nature of quantum computers, these errors caused by noise accumulate throughout a calculation. And so it's generally the case that even if you have 50 or 100 or more qubits, you can't even use all of them, let alone run anything of any depth, because you get consumed by noise. We're trying to help with that. One of the things that you can do is simulate algorithms in the presence of extremely realistic noise, which can help you understand how to make design choices to reduce and or mitigate the effects of that noise, and get the best possible performance out of your quantum processor. For the technical experts in the room, I'm talking about simulation of open quantum systems, Hamiltonian dynamics, which is extremely computationally intensive, even more so than simulating a quantum computer itself, because you're simulating a quantum computer plus the whole system around it, and the exchanges of information between those. So in general, this is very, very hard to do, but it's something that NVIDIA's platform can really help with. So we introduced a capability in CUDA-Q called Dynamics to accelerate this simulation. The kind of previous industry standard software for a benchmark problem we looked at, to run 50 design iterations would take about a year. So a single one would take a few days. Obviously prohibitively expensive. With kind of the full stack that we've built in CUDA-Q, using a GPU, this comes down to 50 minutes on a single GPU, and more on a supercomputer. So really, this is not just accelerating something. It's a difference between being able to do it at all and not being able to. So we're really excited about this. We're already working with some of the leading groups developing quantum computers, including Google, who announced in November that they're using this. They performed the world's largest device simulations and saw these speedups, which are now going into informing future designs. So very exciting, exactly what we're trying to do, and we're going to continue to build on this and work with other groups. The second one is about using GPUs to accelerate or to make quantum computers work better in real time by solving a problem called quantum error correction. Quantum error correction is what you do about the fact that even if you design around noise, you can't fully mitigate it. And so what you need to do is correct errors in real time. And Kazra and Jonathan are probably going to cringe, but I can't get into the technical details of quantum error correction in the 5 minutes I have left. But suffice it to say, it also takes large amounts of classical compute coupled with low latency. And so what we've done is build an architecture to enable anyone to tightly couple their quantum computer to GPUs in a qubit agnostic way, reduce latency by orders of magnitude, and start to run quantum error correction in real time, as well as control the qubits in real time. This is now deployed at the Israeli National Quantum Center. It's connected to a QPU from a company called Rigetti Computing. We've run initial benchmarks showing that we're able to get round-trip latency doing operations on the GPU in under 4 microseconds, which is much, much better than kind of previous state-of-the-art, and below the threshold for many modalities where you're now able to run this on a GPU instead of just an FPGA. We've also showed that we're able to use a reinforcement learning model to calibrate a qubit in real time. What's been done so far is trivial for a quantum engineer and something that's not super hard, but it was also an out-of-the-box OpenAI reinforcement learning model. So frankly, it's amazing that it worked at all. And what we're really excited about is building dedicated quantum models based on quantum data, where we train on noisy quantum systems and simulated data of noisy quantum systems using our simulators, and then using these models to calibrate, control, and correct errors at scale, which is something that no other platform will be able to do. So, we're just getting started here, but very excited about it. And groups around the world, beyond the ones on the first slide, are building with us, which we're very excited to see, including in Denmark. So last year, the supercomputer Gefion was announced. This is part of a few efforts, including Denmark's national AI effort, as well as the National Quantum Computing Program in Denmark, which is a 12-year effort to build a fault-tolerant quantum computer based in Denmark. So we are, Gefion is a supercomputer. I think it's now in the top 20 in the world. And so it's very exciting that they now have a dedicated resource for this. They're going to use it for running simulations like the ones that I talked about at scale, and training these models on the quantum systems that they're building to calibrate, control, and correct their errors. We are collaborating deeply with them, also working with many of the other partners that they're bringing in, and very excited about this as a leading national quantum initiative, and really a model for the world. So that's a whirlwind tour. You can find out more here. If you're interested in checking out our software, you can follow these links, get this QR code, and we have something very exciting coming up in a couple weeks that I'd be remiss if I didn't pitch, which is our GTC conference. This is Nvidia's big yearly conference, and this year there's a huge focus on quantum. So we're going to have fireside chats with our CEO, Jensen Huang, and the CEOs or leaders of all of these groups. We're going to have about 10 more talks from groups who are using our platform to do cool things. I'll give a talk where I'll share more news than this talk, and we'll have, generally a bunch of exciting news all around. So if you're in the area, please check it out. If you're not, it's free to it's free to view virtually. So yeah, link is at the very bottom. So with that, I'll pause, and I think we have a minute for questions, or we're going to go straight to the panel. Okay. Well, thank you for your attention.
Thank you, Sam. I believe you're joining the panel, right? Yeah. So I'll ask you to stay. So thank you, Sam. Now we're going to take the discussion further with distinguished panel of experts who are shaping the quantum landscape across industries, research, and venture capital. And leading this conversation, we're thrilled to have our own moderator, Diana Fabian Nielsen Davis, Senior Innovation Advisor at Innovation Center Denmark.
Thank you for the talk, Sam, and also thank you for those quantum jokes in the beginning, Marcus. We have to work on those a little, I think. But I would love to invite our panel up here. So Sam, Jonathan, Lars, and Kashra, where are you? Please come up here. So as Marcus mentioned, my name is Diana, and I work for the Danish Innovation Center here in Silicon Valley, where I'm part of what we call our emergent technology team. So we work across AI, dual use, space, and quantum technologies, where we build strategic partnerships between Denmark and the US. And I'm extremely excited to be here today to talk about one of my favorite topics, quantum. And I'm very honored to have a really amazing panel that I will be introducing in a little bit. But maybe just to set the scene for our next 35, 40 minutes here, quantum has gotten a lot of attention recently, especially in recent years, where we're seeing a lot of governments, businesses, ventures dedicating billions of dollars into the field. So today we're going to talk a little bit about why that is. So we will look into what is the current state of quantum. We will take a little bit into the future. And then we'll also discuss how can the Nordics and the US collaborate even further on this agenda. So I hope you're up for that. And with that, let me introduce our amazing panel. And maybe just an audience disclaimer, there's going to be a lot of very long and fancy words coming up, but we'll break those down a little bit later. So we'll start with Dr. Kashra Naruzi, who is a scientist and head of hardware at DOE's Advanced Quantum Testbed at Lawrence Berkeley National Laboratory. And Kashra, he oversees the development and the deployment of the full-stack superconducting quantum computing efforts, right?
That was fantastic.
Kashra also has a PhD in applied physics from Berkeley, and before that you were also at the Advanced Light Source at Berkeley.
Yes.
So welcome, Kashra.
Thanks, Anna.
Next up we have Lars. Lars is the founding partner of a venture capital firm called Scale Capital, specifically dedicated to helping Nordic startups scale successfully through the US. So Lars is both an entrepreneur and investor himself and has had decades of experience with expanding and scaling companies internationally and also in transatlantic networks, specifically with the US and the Nordics. So a big welcome to you, Lars.
Thank you.
We have Dr. Jonathan King, who is a co-founder and chief scientist at Atom Computing, where you run the company's efforts in simulations and quantum error corrections and applications. Is that correct?
That's right.
And Jonathan has been with Atom Computing since, I'm losing this. Oh, you should have told me. God. Usually I speak, that's much better. Usually I speak loud enough, but. So Jonathan has been working with quantum computing for over 15 years. Has a PhD also from Berkeley and has published numerous scientific papers and also has numerous US patents. And Sam, we got a bit of an introduction from you previously, but the group product manager at Nvidia, where you're responsible for computing product roadmaps and strategy. And prior to that, you've also been at Rigetti and Keysight Technologies. And you also, like Kashra, have a PhD in applied physics, not from UC Berkeley, but from Stanford.
It's good to be back.
Right. So with these quite impressive resumes and introductions, I want to maybe get a little bit of a better understanding of what they actually mean. So my first question to you would be, in your own words, take a moment to explain how do you work with or what does quantum technology mean in your respective field, maybe using an example or a brief analogy. So should we start with you, Kashra?
Sure, I'd be happy to. Can you hear me? Yes. Okay. All right. Yes. So as Diana mentioned, I work at the Advanced Quantum Testbed at Lawrence Berkeley National Lab. So the AQT is one of two DOEs, that's U.S. Department of Energy, quantum computing testbed programs. We are the superconducting testbed. There's another one called QScout that is a trapped ion testbed at Sandia. So our role has been since 2018 to develop and deploy full stack superconducting quantum computers. And what I mean by that, by full stack, that means everything from the quantum processor itself, which is the chip, the device that encodes and processes quantum information. So we do a lot of work exploring the design space for the architecture of that processor at the smaller scale, but different architectures instead of committing to one as industry does. And then we publish the results so that the community can learn from our efforts. Then there's the cryogenic stack, and there's a control system, which is probably the most strategic part sitting in the middle of the stack. That basically generates the pulses to operate on the quantum processor. And then we have the soft layer on top that is the measurement protocols for characterization and mitigation of noise and error, and the software. So that is the full stack of a quantum computer. We develop all of that mostly in-house, but some of it in collaboration with our partners. And then we make it available to folks from the community, both domestically in the US and internationally, and that includes not just academia, but also other national labs and industry. So anyone who requires deep access to a full stack quantum computer in order to develop and demonstrate their ideas and potentially productize them. And so we've had a history of working with them. So that's the bulk of what I do at the AQT. I also have my own research team that I've been developing, and that centers around exploring the architecture, the proper optimal architecture of a quantum computer, how to do the system engineering development of the full stack quantum computer.
Thank you, Kashra. Lars?
Yeah, so we are attacking this from the commercial side and investing side. So we've been tracking this area for the last 3-4 years. And I think today it's something like 1% of the world's venture capital going into to the quantum area. Whereas for AI, I think it's 35%. So I think we are starting to see that the quantum area gets more and more investable. At least that's what we see in the Nordics. I still think that capital is lacking, certainly in the Nordics for this area. We started investing last year, and we're seeing a lot of exciting projects. So our part, not being a quantum physicist, is more on the commercial area, so trying to see how the applications can be actually marketed and sold in the various applications, basically.
Thank you, Lars. Jonathan?
Sure. So I'm founder at Atom Computing, and so we're a company, so similar to Kashra, we're building the quantum computers. We don't use the phrase full stack that much, but it is essentially what we're doing, like from the actual physical device all the way up to the level that the user would interface with it. The specific technology that Atom is working on, it's kind of in the name of the company. The qubits are atoms. Sometimes we use the phrase neutral atoms, which might sound like a funny qualifier to put on it, but that's to distinguish it from trapped ions, which are also atoms, but they're charged. The sort of philosophy behind why we started a company to do this is that we really wanted to focus on what we believe to be the scalable technology that long-term is going to be useful. And like Sam mentioned earlier, the big challenge in quantum computing, really for everyone, is dealing with errors and just sort of the intrinsic error rates that you get from most of these physical technologies are just not good enough on their own. So you have to focus a lot on error correction. In order to make error correction work, you need a lot of qubits because there's some overhead. You need to encode one bit of information in multiple bits of actual physical things. So I won't get into the technical weeds, but the reason we chose to found a company doing neutral atoms is because atoms trapped by laser beams in vacuum chambers is a really scalable technology. And since we are a company, like kind of Kazra mentioned, we do focus in on kind of that particular architecture, and we're placing our bet on that. And a lot of what we're actually doing kind of day to day is figuring out the physical ways to build these things, to scale them up, kind of the architectural designs of how this hardware interfaces with error correction and the kind of the higher levels of the software stack. And yeah, I think that's pretty much the summary.
Thank you, Jonathan. Do you want to elaborate, Sam? And
Well, yeah, I already said a bit. Maybe I'll just add that I don't know if I said it explicitly, but we're not building our own quantum computer. One of our philosophies is if somebody else can do it well, we shouldn't be doing it. And you know, the world's experts, including some of the people on this stage, are doing that. Our approach is to figure out what Nvidia can bring to the table that no one else can bring, or what Nvidia can bring and do much better than anyone else that's useful for quantum, and then partner with groups like this to help them be more successful and successful faster.
thank you, Sam. So thank you for sharing a bit about your work and focus areas. The next thing I want to touch a little bit upon is the current state of quantum. I feel that in the media at the moment, both within the last months, but also within the last weeks, we've been seeing a lot of groundbreaking news coming out on quantum. We're also seeing some really, really high venture funding announcements. We're seeing some quite high valuations from startups going into strategic partnerships with governments and other partners. So my question to you would be if you could, in simple terms, share what some of the latest advancements that you've seen in quantum that you find particularly interesting. What is some of the things that are coming out that you find are really interesting? Anybody wants to take the floor on that?
I mean, I could start. I mean, because it sort of plays off with what I just said. I think the current status of things is that there's sort of this transition, which I think was always recognized among experts in the field, but now the results are really coming out about doing error-corrected, larger-scale quantum computing. I mean, of course, I would highlight the work we've done on this, but you know, even recognizing what's gone on at Google and other places, for example, showing for the first times that you can actually drive error rates down by scaling up the distance of error correction codes. And it's sort of, I think, sort of a focus shift maybe away from doing what we can with the noisy quantum computers that do exist towards really driving towards what are the not so noisy quantum computers that we need to have in the future. And I think the focus of the last few years, people working on that is now starting to show up in both academic and industrial results that have come out in the last year or two.
Thank you, John. Cash, what did you have?
Yeah, so I echo that sentiment. For sure, the most important news over the last year has been multiple demonstrations of error correction, scalable error correction. And to build on top of what Jonathan was saying, it's important to note that it wasn't just one or two companies doing it. We suddenly had a deluge of multiple companies based on different architectures showing different ways of implementing error correction. And it's important to note that we shouldn't really take it for granted, because if you look several years back, 10, 20 years back, there were a lot of no-go theorems that postulated that we'll never be able to build a functioning quantum computer because as we build things larger and larger, noise will actually scale unfavorably and we'll never be able to suppress it. And so now that's not a concern anymore. We know that we can do it in a lot of different architectures. But, so that's all good news. One thing to temper that a bit is also, I remember when, well, I don't want to single out individual companies, but when a couple of these companies were coming out with these news over the last few months, a lot of people came to me and asked, "Well, this is really huge, right? Now we're going to have immense applications and quantum advantage in the next year, whatever." And really, that's the thing to keep in mind is that this was really, they hit their milestone, right? It was on their roadmap. It was expected that they would do it. It was more like a sigh of relief that we are making progress toward our goal. We are accomplishing things we promised we would. And so it's basically, from my perspective, things are just healthy, right? It's not that we don't have really cause to be worried about whether we can do it or not. You know, there's a lot of other scalability bottlenecks to resolve, but the fundamental issues, some of them have been addressed. At the same time, it's not really a huge breakthrough either. So my summary is that it's kind of healthy and we can be relieved about continuous progress over the next few years, hopefully.
Sounds good. Sam Larch, anything to add?
Yeah, no, I echo that. I think, even 1 or 2 years ago, the things that were getting the biggest news in quantum were these demonstrations of comparisons to supercomputers on problems that were not useful and will never be useful, and were kind of amazing demonstrations of the technical ability of the teams that did them, but not on the ladder we needed to climb. And I feel like now we've jumped to the ladder that we need to climb and are climbing it. And yeah, as the other said, not just the biggest companies in the world or not just one modality, but startups, some of whom were incorporated pretty recently, and many different modalities. So that's very, very exciting.
Very cool.
Important milestone, I think, for getting more funding into the area.
Yeah, definitely. And maybe could you also provide some examples or use cases of how you're seeing quantum being applied today? You presented a few cases, Sam, in your presentation, but where are we with quantum in like a practical aspect? Like how are we seeing it being used today? Are we seeing it being used?
We're focused on making the quantum computers better. So it's almost like for us, the quantum computers are the problem. I mean, I think I'm not as close as some others, but we're maybe in the experimentation phase, and the hardware is not ready yet for real advantage, but it is important and valuable to develop better algorithms and understand where quantum will be useful and where it won't, so that we don't have a situation where these guys build an amazing million-qubit fault-tolerant quantum computer, and then it takes many more years to figure out how to use it. So I think there's valuable experimentation happening at the very least.
I could add a little to that. I mean, like as of today, the main use case for quantum computers today is to drive innovation around quantum algorithm discovery, understanding what you can do with quantum computers. The biggest customers are largely national labs, academics, institutions, where doing scientific research is the product they want to deliver. And so I think that's the main value today, and that's largely I think both domestically in the US and other places who you see spending the most money on quantum computers today. Like as Sam mentioned, I think the problems for which quantum computing seems to be outperforming classical computers today are these sort of basically just solving random problems that aren't really applicable to anything, that are just constructed as a test for showing that the quantum computer can do that. So I think that's the sort of progress. I mean, that's sort of the state of things now. But I would point out that along the lines of what I said, driving innovation and algorithm use case development, I think Sam talked about this, I think is really important, because there's some big applications, like probably most people here have heard about, a quantum computer will eventually, break RSA 2048 encryption or whatever. The quantum computer that can do that is a lot bigger and more powerful than the quantum computers that can exist today. Kind of what can we do before we get there is a little bit harder to figure out, because people don't yet have or haven't had the access to the hardware to sort of iterate and figure out what quantum computers can do. So I'm personally pretty interested in, what's between today and these sort of lighthouse applications that we know will eventually be available, but the intermediate zones are kind of underexplored. And so to wrap that thought, it's the main purpose of quantum computers today is to explore that area.
Yeah, just to add to that a little bit, I'm really glad that Sam and Jonathan took this first. It can be a third rail to talk about the application, especially because there are so many companies that very boldly claim that they are really doing applications of quantum computing. And from my perspective, when it comes to applications, we are in the era I would like to refer to as quantum for quantum. Really, we're not doing anything beyond that. We're engaged in the pathfinding phase, whether it's about molecular simulations and dynamics or logistics or mathematical applications and encryption. Everything that we're doing is really pathfinding, and it's really helping the community develop their intuition for quantum algorithm development. And since we also talked about error correction now, it's also important to know. So at AQT, we also work with application and algorithm developers a lot as well, and those who are characterizing and mitigating sources of noise and error before and during error correction. And one of the things they always like to drive at, and one of their biggest pet peeves in the discourse they hear publicly, is that it is never acknowledged that whatever type of algorithm and application you develop for the NISQ era, for the current noisy era quantum computers, has really basically nothing to do with error-corrected, fault-tolerant algorithms. That's a whole different beast. So, but the point is, it's not even going to be an incremental progress towards something that really works. We're just trying to help each other learn how to navigate this path that will take another 10, 20, 30 years.
So I guess it's fair to say that the stage we're at now is still experimental and for research. So to move things a little ahead, I now want to ask you the $1 million question that I'm sure you have gotten numerous times, and maybe you have also answered it differently throughout times, but when can we expect to have a commercially viable quantum computer? So earlier today we had Ari from the NATO Innovation Fund up, and he said he had a very clear answer to that it would be everything from 3 to 30 years. So maybe you can shed a bit of perspective on when I'm going to be able to pull up my quantum computer and do algorithms on it.
So maybe I'll take this one first, just to build on top of what I already just said. The answer is that it is highly, highly dependent on the application. The applications that involve simulations of nature, things that inherently involve complex degrees of entanglement, such as simulating molecules for drug discovery and pharmaceuticals or material discovery, things like that. Those are generally believed to be the first ones up, meaning they will require the fewest numbers of error-corrected qubits to simulate. And so that we may arrive at in, 3 is really pushing it, but 5 to 10 years, it's believable. We might arrive at it then. And then on the other extreme, we have things like encryption breaking and whatnot, and that is, it's probably 20 years out, and by the time we get to 20 years, classical encryption will probably evolve a lot more as well. Depending on the application, 3 to 30, sounds about right, and so that is the caveat, that is the detail.
Okay.
Yeah, I guess running a company that builds hardware, I would say similar thought process. I think we have maybe a more optimistic view on our roadmap for getting to those milestones, but I think I would lay it out like, if you're, it's sort of echoing what I said before, if your current application is to drive research and development and, allow your scientists to do good work and do publications and get grant funding for your national lab and your university, the answer is now. If you want to break encryption, that cannot be like 2048-bit RSA encryption. That one is going to be much farther out in the future. I think it really, really does highly depend. Like, we just now, kind of in the recent couple years, have seen quantum computers, like Sam mentioned, that do things that classical computers can't do. Problems that have names like random circuit sampling, things like this, which are sort of just scientific problems with no application. Where error-corrected qubits will start doing things that a classical computer can't simulate. I'm optimistic that does happen in kind of the next 5-year time frame, and then so you start thinking about what are the first applications in simulations of materials and chemistry and things like that could be simulated on that sort of system. Yeah, I'm pretty optimistic on that sort of time frame. The big, I'm going to simulate. I'm going to fully simulate molecules that require thousands of high-fidelity qubits or things like that. Those are the ones that are, a little bit beyond that 5-year time frame, most likely.
Okay. Sam, any take from you?
I'll maybe join the group in not giving a single answer. It's really hard to even think about as someone whose focus is making it happen as fast as possible, because it, obviously it depends on how hard we work and how well we do our jobs. And, there's also the bit that breakthroughs by their nature are hard to predict. I do agree that it's going to be a continuum where there are problems around simulating physics or simulating physical systems that quantum computers are well suited for, that will come first, and many other applications that will come later, and where you define commercially useful may vary.
Thank you for that. And then Lars, I wanted to ask you, so as an investor, how do you navigate in this uncertainty of investing in something that might be everything from 3 to 30 years or unknown? Because you have invested in quantum companies, so,
Yeah,
so how do you navigate
that's
it?
the reason why it's really tough as an investor. But I mean, we look at applications that are sort of quantum ready, but running on supercomputers, and actually building applications that are used now, not in 13 years. So that's what we try to invest in. So especially in the biotech, pharma space, drug discovery, drug development, there's already now, things you can do that can speed up the processes. So yeah, we're not taking bets on something 5-10 years out at this stage, because we don't know what it's going to look like.
Mm-hmm. So kind of looking into applications that are already now being useful.
Yeah.
All right, thank you. So I hope it's fair to say that while we are seeing a lot of progress, there's still going to be some time before I can pull up my quantum iPhone. That's going to take a while. So for my next question, I would actually like to see how many in the audience here work with quantum in some kind of capacity. So maybe by raise of hands, is there anybody here in the audience that works quantum? A few? Yeah, so not so surprising, not too many here today work directly with quantum. So my next question would be for you, for all the business leaders that are here today and that are not directly working with quantum, what can they do to educate themselves, and why should they care? Should they care?
Really depends on what their interest is, right? If you're involved in a company that is doing drug discovery and things like that, obviously you need to be very tightly coupled to the community to understand how to prepare your company. And most of the large corporations at this point, whether it's for materials and pharmaceuticals or logistics and automotive and whatnot, and even aircraft companies and whatnot, they have hired teams, and finance, they have hired teams of algorithm developers for quantum, and they're basically developing their own core expertise in-house to stay aware. There are a hierarchy of resources available in terms of communication with the experts, in terms of publications in consulting, McKinsey and BCG and all these companies, they have briefs and things that come out. I think really the answer, unfortunately, in this case also, is there is no single answer. It really depends on what your interests are. Anywhere between hiring your own team and building your own expertise, having quantum experts on your boards, communicating with experts, or just reading the resources online. Any of those could apply to you depending on why you're interested.
Any others?
I would say just on a very high level, starting with Google and Microsoft to see what they're doing. I mean, as a business leader, knowing nothing about the field, watch some videos, just get a sense for what this is. And then, as you said, deep dive into, if you are in biochemistry, or then look at the leaders within that area that are working on quantum. There's a lot of information out there, so there's no excuse really not to dive in. Yeah.
Jonathan, Sam?
Yeah, I mean, I would just echo we talked earlier about where we thought the first really, really useful commercial applications would be. We said chemistry and material science. So I would say, for large companies that are in kind of those fields, I mean, most of them probably at this point do have these sort of quantum, like they hire quantum computing PhDs to sort of develop strategy. So, if you are in a business that is big enough to afford those kind of resources, now is a good time to do that. If you're, kind of smaller, then probably just tracking what other people are doing in the domain is the right way to go.
I think people should care. It's really exciting. It's really exciting to me. All of the largest companies in the world have invested in quantum in some way. It may not be relevant for your business on the horizon that you want to put resources into it, but it may, and it's worth at least understanding it and talking to experts and educating yourself, in my opinion.
Thank you. So we looked a little bit into the current state of quantum and the future, and it seems there's still a lot of work to be done. And what I'm also seeing and hearing is that in order to actually succeed, this also demands great collaborative efforts. All of you are collaborating in multiple ways with different stakeholders to make this happen. So I think I would like to tune a little bit into these collaborations and talk about the Nordics and the US. So maybe an open question to you: what strengths do you believe that the Nordics can bring to the table in the field of quantum, and how can these complement the capabilities of what we're seeing with the US industry and research and venture?
The Nordics have and have had for all of the history of quantum some of the strongest quantum research and researchers and leaders and groups in the world. So there is incredible expertise and talent in the Nordics. I'm most familiar with the effort in Denmark, but I know there are major efforts in the other Nordic countries as well. And the effort in Denmark, I think, has one of the kind of most smart strategic roadmaps, attitudes about collaborating with other leaders around the world and leveraging the best of other technologies, and then building the parts in-house that they think that they can do the best. So I don't know if I have any. I don't think I have any notes. I think the Nordics are going to lead in quantum.
Yeah, I mean, for us, it's public knowledge that we've been invested in by the Danish Sovereign Wealth Fund, and we are setting up an office in Copenhagen. And so, I would just say, number one, just having that, a community or like an ecosystem for investment in quantum is clearly very strong there. And kind of the support we've gotten, as Sam mentioned, there's a good talent pool there. As our company, we need to get a foothold in the European market in general, and Denmark turned out to be the most welcoming place, and the people we've been introduced to there. There's clearly a coherent effort to kind of foster this sort of development there, and so that's just made it a really easy choice for us to kind of establish our European base there. So yeah, I think just sort of this coherent effort across many different organizations, government and otherwise, has just made it an easy choice for us to invest there, or to set up our offices there.
I also think we're blessed by the history of the Niels Bohr Institute and all the research that has gone on for many years. And we also have Novo Nordisk, one of the largest companies in Europe now, spending a lot of money in this area. And then Jensen and our king is making things happen. So I think it's very exciting.
And Kashra, I know that you've been on a big Nordic tour last year where you visited both Denmark and Sweden and Finland, and not only for the great weather and the delicious food, but you were also exploring potential collaboration. So yeah, maybe put a few words on that.
So yes, I am deeply biased. Thank you, Diana.
Putting that out there.
But yes, so I mean, just by way of background, yes, I've developed over the last few years. I've developed two partnerships in the Nordics, one with IQM in Finland, and one with the Novo Nordisk Foundation Quantum Computing Program with Peter Kostrup and the team and the rest of and other folks in Denmark. But this is, I mean, it's important to point out why that matters. Because I've also been forming other partnerships and collaborations with other Europeans as well. But what sets the Nordics apart is you have really coherent strategies. Denmark in particular has had a really nice, well put together, all-encompassing coherent strategy for quantum. Overall, the Scandinavians are open. And obviously that is partly cultural, but it seeps into other aspects as well. So for example, with IQM in Finland, They have been one of the most open corporations in quantum that I have seen. I remember when I was having the initial conversations with them a couple of years ago, what's really stuck with me was that, when they sell anyone, we haven't bought a quantum computer from them, just to be clear. But when they sell anyone a quantum computer, they give them the source code, and folks are welcome to play around with it and modify it as they want. And I don't really know of any other company that now. The ones that I have looked into, let's say, right, that are that open. So that spirit of openness, of course, it exists with Peter Kostrup and the academics in Denmark and other countries. But even with the corporations, it exists. So, and then lastly, that cohesiveness means that when I'm engaged in discussions with Danish entities or others in Sweden and Finland, not so much Norway yet, but I'm, if folks, yes, yes.
To be continued.
I know that you guys are yes. But I know that when I talk to anyone, the rest of it is also, the rest of that community is also aligned. That alignment is important. What was missing was kind of an alignment between the different Nordic countries, and as you know, I've kind of pointed that out over the last few years. But I see that there's a move towards better alignment of the Nordic countries amongst themselves as well, which I think is needed for a better power projection by the Nordics as a cohesive entity. And so that is going in the right direction as well. So, the point, in summary, whether it's about the technicals or good advisement or cohesion or the culture of openness, all of it it makes it a really good opportunity for collaboration and partnership.
And don't forget being the world leader in people named Jensen, which is very appealing for us.
That definitely also counts. Well, it's great to hear that there seems to be good and continuous opportunities for the Nordics and the US to do even more on this agenda.
Yes.
So I still have a lot of questions that I would love to answer and pick your brains on, but we have around 4 minutes left. So I would actually also like to open the floor to you guys here on stage and ask if there's any question that you have burning for your fellow panelists now that we have all of you here. So if there's any of you who has a question you would like to ask the others, now is your chance. Else I have tons.
Maybe if I can push Lars here a little bit more
on the technical,
on the investment question. So how do you see over the years, I mean, you've been in this area for a while, how's your, a few years ago I remember there was this attitude that there's not enough expertise and advisement for investors, and so they don't necessarily, it's harder for them to make investment decisions. How has that been changing? How do you keep updated? How do you make your investment decisions? And how do you see the opportunities evolving over the years?
So I think for generalist funds, it's impossible to invest into this space. So we see now over the last 5 years, we've seen quantum specific funds that only do quantum and pretty much invest in everything that is out there just to have a better chance of hitting the right ones. But no, it's really hard. And we have, fortunately, a good friend and advisor in Kurt Stockbro from Sparrow Quantum, and also Mark from MQS that we invested in. So we have people that are close to us that can advise us on the latest developments. And I think there's a lot of resources out there. As I also said, there's no excuse not to follow this area closely because it's a very collaborative and worldwide community of scientists working to solve this problem. So, but it's for a layman, a non-PhD, it's tough.
Thank you, Lars and Kashra. Anyone else? Else I have a question that I would love to answer or get your take on. And you also touched a bit upon it in your talk, Sam. I think it's almost impossible to talk about anything today without talking about AI. As you mentioned, Lars, I think it's 37% of venture funding went into AI last year. That's over $100 billion US. So maybe talk a little bit about how you actually see the intersection between quantum and AI. Is this something that is, are they like two pots in a pan, or how do you see that intersection? Where are the most significant opportunities within this?
I could say a couple things. I mean, there's the obvious answer, which is it seems like AI is useful going this direction. AI is just going to be useful for so many things. Like anybody doing technical work, is going to use AI to accelerate what they're doing, whether it's just writing code or whatever. But so I think that'll be true for us as much as anyone. It's interesting, like quantum computers, even when we're talking about thousands of qubits or like millions of qubits, the amount, like that's a small number of bits. So it's kind of like the amount of data going in is relatively small, but the computation is very difficult inside. And that's not exactly the same as AI, where there's much higher amounts of data moving around. So it will be interesting to see how these things come together in workflows. Using data from quantum computers to train AI, I think is something that's interesting that people are talking about these days I'll just say it needs to be explored farther because that's interesting. It's really interesting.
So yeah, I can talk about this a little bit because we've been looking at that problem for a couple of years now, and we've actually done some stuff and published some stuff in this area, and we will, there will be more to do with Sam and Nvidia and Keysight and others who do ASICs for AI, and that is the problem of architecture of quantum computers, as I mentioned. The piece that's in the middle of that stack is the control system. And that's typically FPGA based, and it interfaces between the algorithms and applications together with the quantum processor at the bottom. And it has often been ignored, how much potential there is there. So the team that I've been building, that has been the focal area for the research over the last couple of years. And we've already demonstrated through deep co-design of application algorithms with the control system that we can achieve order of magnitude improvements. But one in particular was, it involved deploying a lightweight machine learning model on the FPGA board, just the classical resources that are available there, to learn, in particular, a term called quantum state classification. Don't worry too much about it, but it basically improves your quantum computations. And notably, what we discovered is that we are limited. We really need low latencies, way faster than what Sam has already. I mean, it's great that Nvidia is going in that direction, but 4 microseconds, we need something on the order of less than half a microsecond, right? But if we can have classical resources of the computational power of a GPU, let's say, or even a tenth of a GPU, doesn't need to be that high, but really with low latency on the control system, there's a lot that we can do beyond just error correction. And so, we're a couple of years in, we know where we need to go, but there's a lot more work that needs to be done. Suffice it to say that AI and quantum are really deeply intertwined at the architecture level.
Very good. Thank you so much. And I can see Rebecca is looking at me, so so with that, time is unfortunately up. I hope you all got some insights on this fascinating topic, and let's give a big round of applause to our great panel. Thank you, guys.